Hi everyone, my name is Pat Hickey. I work at Fastly and I'm the tech lead on our LibC WebAssembly compiler and runtime. If you care, these slides are on GitHub. I probably won't be able to read that, but okay, and so I'm here to talk about WASI, which is a standard that is being worked on by the WebAssembly community group. It's an open standards group. People from the Bytecode Alliance are involved and many people beyond. WASI is a modular systems interface, and systems means the stuff you usually find on a desktop application, like your regular Unix application, LibC, and it can mean all kinds of things beyond that. We're not trying to be restrictive to this is just POSIX or just things that are compatible with POSIX and Windows. We want it to be a big tent of interfaces as long as they are useful to people, to multiple WebAssembly implementations. We want to have standards that help you be compatible no matter where you're running. And WASI has two focuses we care about. Security, and this isn't the best talk for that. I'm not going to be the expert to tell you all about capability-based security systems. We are building things as a capability system for principle of least privilege and all that good stuff. But that's a separate talk. And portability, we care about this running on many host OSs, on many WebAssembly runtimes, and in many different kinds of use cases. So whether that means down to microcontrollers with Intel's WAMR runtime. Fastly is working on a serverless offering that's going to be based on WASI, and Mozilla has it working both in and out of the browser on the WASMtime engine out of the browser, and they have polyfills to make it work on JavaScript in the browser. And several other engines have implementations as well, including WASMer, Node.js, and probably a couple others I can't remember off the top of my head. So the two big question marks between what we want WASI to be and what it started out as, I think, are modular and portable. The goal of WASI is to be modular, meaning that you can implement certain portions of it or say, oh, this system doesn't have a file system. But WASI started out as just one big system. It was one big WebAssembly module called WASI Unstable. The name was very deliberate to give you no promises that it's staying in its current form. But it was just one big module. And the goal was to make it many different modules, and that supports making capabilities of what kinds of things you can access and do much finer grained, and to make certain systems be able to support certain segments of it. So the kind of the tip of tree part of WASI, the most recent merged developments that aren't officially supported by runtimes yet, is called the ephemeral version. And we actually just merged Dan's PR that split that one monolith module into 9 modules. And so that's like one way in which we've made a breaking change to WASI. Code that was compiled against the one big WASI Unstable module would now import things from all those 9 different modules if it used the whole interface. And that's one example of what kind of changes we're going to make in order to refine the interfaces to be finer grained. The other thing is portable, and portability means what sort of host systems it runs on, whether that's all the various WebAssembly runtimes I was just listing, and also what languages inside of the WebAssembly sandbox can use it. And of course, WASI started out as a C header and a LibC implementation that was built around that. So it didn't start out as very portable at all. It was start out as for C programs only. And then Rust built its support on top of that LibC. Thing is, specifying a standard in terms of a C header isn't really portable. It just happens to be like what that particular compiler does today, and the next version of the compiler may choose to do something a little different. And it doesn't really do anything to help people trying to implement it for other languages. So that's one of our big goals, is we made a more friendly machine-readable spec that's not just a big bunch of C preprocessor. The actual binary compatibility, like the calling convention, how you represent arguments, is still tied to the way C language does things. We have a plan for that. It's not going to be like that forever. And the plan is called interface types. And that is also not this talk. There's a lot of people in this room who are more qualified to speak about that than I am. The great thing about WASI is it works. Before WASI, Fastly wanted to run C programs on our runtime, so I cooked up something that was really bad and didn't work very well, but like it could print hello world, but sometimes you would hit a bug, and I didn't know how to debug it, and it wasn't my job, so I just kind of left that aside. WASI is simple enough that it works, and it's simple enough that we were able to adopt it quickly. From the time that Dan first reached out to Fastly and told us about this new standard he was working on, sorry, when I say Dan, I'm talking about Dan Goman from Mozilla over there, who's the lead of the WASI working group. But from when Dan said, hey, I've got this cool new idea called WASI, to when we actually had a working implementation that, you know, basically did the hello world. It was like about 4 days, which I thought was really impressive, and part of that is like all the great code reuse that Dan had in the LibC that we were able to use, and that Yuri did a great job with build scripts and all these things. Like, it was a lot of great work on Mozilla's part that made us really quick to adopt it, and since then we've been contributing to it. The thing about adoption is we also need to evolve WASI, which means constantly changing it, and we of course want to continue adoption and get other languages that are coming to WebAssembly on board and other runtimes on board. Those two are at odds, right? Like, you can't adopt something that's changing quickly very easily. So I said we came up with a computer-readable way to describe this interface. We call it WitX, W-I-T-X, and that stands for WebAssembly Interface Types with Extensions. So I said this isn't really a talk about interface types. I'll give you a little bit more details of that as this talk goes on, but this is an aspirational language that one day will reflect the interface type standard that's still under development and is in some ways like not as complete yet in terms of working as WASI, but it's going to change the world. So we're willing to wait, and we're willing to incrementally evolve WitX to look more and more like interface types as the spec is ready and as implementations are ready for it. So we created this language, and the specification written in this language is for WASI. That's the first specification, and then, you know, Fastly has some custom stuff that we have essentially as prototypes, and we describe those using WitX as well. So it's good for more than just WASI, but essentially this is the one place where it gets used. So I'm stealing this term from Alex Crichton. Developer stability is something we care about. How can we help you adopt it and help you keep up with all the changes we're making to WASI? Like I said, we've already made some changes, and we have many more to come, and those are going to do things like change some of the concepts around how files are treated to not be as tightly coupled to POSIX, which is good for portability. It'll be good for security of like, oh, this is a file that you have to treat as a stream, and you can't do the bucket of bytes operations on it that you might, so you have to treat things as a more generic term. You have fewer options to operate on it. So you can expect to see more of those kind of changes coming. But the implementers are also saying, well, we're not just going to throw away the old version of WASI every single time we have a new idea. We're going to keep on supporting old editions. And I think we're going to be good on that promise, because at the moment, those groups have a huge overlap. And in fact, many of them are in this room right now, which is really cool, because we were meeting earlier today, or many of the ones from the Bytecode Alliance anyway. We need to, as we make changes, keep both of these concerns in mind, because kind of like both of them are our job. And that means we're going to design evolution with polyfills in mind. Polyfill is just a way of saying when we have a new standard, we're going to also provide, as straightforward as we can, a way to implement the old version of the standard using the new one. And WitX is designed to help that. So what does a WitX specification look like? And this is the part where I show you some actual code. WitX is, first off, it uses S expressions as a syntax. We did that because there's precedent in WebAssembly. The WebAssembly text format uses S expressions that look just like these. We tried to just follow that lead everywhere we could. So identifiers start with $signs, reserved words don't have anything in front of them, and new words that aren't really in the standard yet have an @ sign in front. So that's the interface keyword there is lifted from the interface types, and then there's some stuff that WitX has right now, like we have pointers in WitX, and we know we eventually don't want to have pointers because they aren't really portable across languages in the same way that just like saying what a more abstract type is there. So those are WitX specific keywords at the moment. But this is a WitX document that's right off the spec, and there's use statements. You can have parts of the specification in other files, which obviously for reuse is important. And then you specify a module, and the module can say something about the requirements of, like, well, we're going to need linear memory to implement this module. It's kind of all of them at the moment. And that's stolen from interface types. And then this interface function is saying this is a function that we're going to present to the outside world, and these are its parameters, and this is its result type. And the U8 and the pointer there are built-in keywords, and this erno type is actually defined off in the type names file. So what do the types look like? We also have this concept of a top-level construct called type name. And so you can say, oh, this is just a name of a thing. So timestamp just always corresponds to U64s. Or you can structure things a little bit more. So for you have an enumeration. In the original C header, this was a literal C enumeration using C syntax. And this is kind of the X expression version. What it says is that you represent this enumeration using a 32-bit number. And these are the 4 variants. The other thing is that each of these types and all of those enum variants have document comments. And that was originally, the header file had comments in it, and then we made a markdown file that we would kind of try to maintain alongside the header as we made changes. And now, there still are a couple markdown files in the repo, but we're trying to make it so that the canonical location of all these comments, all the human readable information, is right here in the spec file. And you can render that out to Markdown or HTML or whatever you like, or just read it right in there. And so if you were to use this to generate your own enum and your own source code, you would be able to also render out those comments so that in like your C language version or your Rust language version, you could have the comments right there to know what all those variants mean. A couple other types we have. We have enums, flags, unions, and structs. Flags are just like enums, except they're bit masks. You can have many of them. Unions and structs are also just right out of C. They are a set of fields with a type and a name. And so this is how you pass a subscription to events for multiplexing on waiting or blocking for multiple events. So you have this subscription struct. It has a field here that's this event type is an enum that indicates which of these is valid. And then the union is the actual contents of the thing you're waiting on. So that's a fairly standard interface. The next step up would be for this to be an abstract data type where mechanically we would say that, if it's the FD read event type variant, then this must be the enum variant that corresponds to it. Right now that's just encoded in the comments, and that's really because this is still one of those first layers of taking a C header and turning it into something machine digestible. And we haven't figured out exactly how we want algebraic data types to work because there's a whole lot of different ways to do it. So until we do, we're going to keep it this way. And one day we will upgrade these to real algebraic data types. So what is the vision we have for this tool? I already said it's WebAssembly interface types plus extensions. I think I actually already covered this slide. One day we want this to not 100% go away. Interface types doesn't have a concept of giving types a name because it just happens to be a detail of the way the WebAssembly type system works, is that all types are structural. If you have a struct with those fields, it's equal to any other struct with those fields. That's actually a really good feature in a system like WebAssembly, but it makes it hard for you to know how to generate your C header or your Rust module and know what the name to give to that struct is, because it's just sitting there as its structure. So we want to keep names around, and that'll eventually be the only extensions, I hope. The other aspect of interface types is a freedom from picking a particular machine representation of abstract types. The short version of that is, in C right now, anytime you pass a string somewhere, you're going to pass a character pointer and a length as two 32-bit numbers. One is a pointer into memory, one is the length of memory. And that's fine for C programs, but JavaScript programs don't represent a string that way. A string is just some abstract thing. If you want to be able to exchange strings between JavaScript and WebAssembly, which is a pretty common use case in the web, you need to be able to describe to the runtime somehow that, oh, this particular WebAssembly module, to take this particular string, I'm using a pointer and length pair, and that's UTF-8 encoded. And so if you're going to pass that to JavaScript, then the engine knows what it has to do to convert that into whatever internal representation it uses for JavaScript. And then, if you're going to pass it to another WebAssembly module, you're going to look at that module's interface type description of how that string works. And in case it happens to be another C or Rust module that also said, I use a pointer and a length pair for UTF-8 encoded, then the engine is able to make a smart decision and said, oh, I know how to optimize that to a memory copy between the two. I don't have to encode it to some intermediary thing, do some extra copying. So that's the very short version of why interface types is cool. There are many other reasons it's cool as well. Lots of other upcoming WebAssembly features will be able to make it compatible with languages that don't have native support for them and all kinds of good stuff. Okay, so then the tool itself, I said WitX is a language that things are written in, and as far as I know, there's only one tool that knows how to that understands the WitX format, and it's called WitX. It lives in the WebAssembly WASI repo itself under the tools WitX folder. So that's all on GitHub. It's all with all the very nice copyright that the W3C working group assigns to everything, so everybody can use it. And it's a Rust crate because we program in Rust, so that was the natural choice. I would love for people to write implementations in other languages too, because we know Rust isn't the only language that matters. It is both a library that we can use from other Rust programs, and it's just an executable by that same name. So if you want to just install it from crates.io, you can install it with cargo install WitX, and it'll become an executable on your machine. And then you can import it in some other Rust crate if you're writing some more code. So if you use the tool with just its bare name, WitX, and you pass it a specification file, it's going to validate that spec. And so what does that look like? Oh, I gave it away. So here we have the current specification of WASI. I'm using cargo run just to run the version that's locally on my machine, but you would just pass, instead of that cargo run --, you would just pass WitX. And then here's the spec file relative to where the tool is. And that's going to say, I compiled the program, and I ran it, and it gave me no output, which is good. No output on Unix means you got everything right. So let's make a typo, and have it please validate that. And it's going to tell me I have a syntax error, which is cool. It can do more interesting things, like if we put some type here that doesn't exist. Sorry, I keep on going the wrong way. It's going to tell me I have an unknown name. And if I do more sophisticated things to make a type error, it's going to catch those all, I think. So that is just the WitX, how you validate. I also told you about those doc comments. So if you want to render a markdown file that describes WitX, you're just going to, right after the file name there, type docs. So you're going to, well, I better actually fix the syntax, huh? And this is, it's long, but this is the markdown that describes every single type inside of WitX, every single function, every single argument in that function, and so on. So I'm glad that there's documentation. That's really good for accessibility. And here's one way to take it and then make it viewable in a web browser where it actually might be nice to read. And then finally, this is not quite merged into master yet, but it will be soon, WitX polyfill. And what that actually allows you to do is to diff two specifications, and it tells you whether their ABIs are compatible, and if not, where they're not. So this is essentially a tool that is meant for developers like me to make sure that as I implement new snapshots of WitX that I'm getting it right. There's the way where I'm going to print, again, markdown out to the screen. Also, all of these commands are available through the library interface where you can write a Rust program that walks over those trees and does all the right things. So where's the polyfill one? Okay, and so this is the difference between the snapshot 1, the current standard, and the original snapshot 0, which is we keep all these archived. We don't use Git history to keep our snapshots. We actually keep an archive in a directory. And the idea there is rather than using Git checkout to grab all the old one or tags or whatever, we want them to all be available because we expect implementers like me to be supporting many of them simultaneously. And then this argument here says map the module named WASI snapshot preview 1 to the old module name, which is WASI unstable. And so down here, this abbreviates a lot of things when they're totally compatible. And it's saying, oh, in file stat get, the result, the old version of file stat is incompatible with the new one. And that was a case where we had a 32-bit offset into the file. And somebody pointed out, well, files can be 64 bits long. And we said, yeah, of course you're right. And so we fixed it. And then, so it summarizes all the other places where that's the case. And then down here it says type conversions. This is like, if you are responsible for implementing this, you've got to fill in the conversions in all of these call sites. But for the actual types themselves, the function you'll need to reuse to convert them back and forth is you just have to implement these three functions. Turn old wents into new wents, old subscription to new subscription, and new file stat into old file stat. So that's your current maintenance burden, all summarized as markdown. And my next trick is that I want to actually make that generate the implementation for those, just given these three functions. I haven't quite gotten there yet, but I promise I will do it soon. Okay, so who's using WitX? I did kind of give it away that many of them are in the room right now. But here's the actual projects that you might actually be interested in using. So WASI LibC is, like I said, the very first WASI implementation. Originally, this header file was the spec. And now, thanks to Dan's work, he took the WitX tool and he made it generate this header file. He wrote this subcrate called WASI headers, and that's just run as part of the build step of WASI LibC. If you check in a change to WASI LibC, and this ends up being a different implementation, CI will catch it. As you upgrade to a new snapshot, you just point the build script and say, I'm targeting that new snapshot, and it'll tell you all the things. It'll generate the new header file, and then the C compiler will spit out all the places where your implementation doesn't quite match up, to the point where the C compiler is able to, which is not great, but better than nothing. So that's a userland implementation of WASI. It's what you compile a C program with in order to target the WASI APIs versus your regular libc would target your operating system. WASI Common is a runtime for WASI. So this is an implementation that takes that WASI set of API calls and it implements them in terms of Linux, some weird BSDs that have slight differences, and it does almost all of it on Windows. The great thing about WASI Common and the folks that are working on that and supporting it on Windows is that they're discovering ways in which our interfaces aren't actually quite portable. And so that's informing, of course, the spec to change to be, oh, let's actually get so we're portable to Windows. WASI Common is a joint between the Lucid team, the Wasmtime team, and some folks at Golem, which is a blockchain. This one is a Rust crate, so there's a procedural macro, which is a really cool thing in Rust, that generates Rust code as an AST that the compiler can then interpret. And so this WIG procedural macro reads in, it's ordinary Rust code that reads in the WitX spec in the WASI repo, and it depends on the WASI crate, and then it generates out that syntax tree, and that syntax goes into WASI common and makes it all work. WIG, we're going to work on making that emit the boilerplate for functions, and then that's the place where I'm going to make it implement the polyfills as well. And then there's two more. There's a WASI Rust crate. So in the very beginning, I said that Rust was able to adopt WASI really quickly because they were able to build on top of WASI LibC. That was a great way to get it done fast. The ideal way to do it would be to have a pure Rust implementation so that you would have the Rust language's type safety all the way down to the interfaces. So that would be hopefully free of bugs that might sneak in a LibC. So that's something that Alex Crichton's been working on. There's a generate raw crate, and that generates actually the entire crate. So you point generate raw at the right specification, and the entire WASI crate pops out. There's actually, well, there's like 20 lines of code that defines an error trait, but I think we'll let that go for now. So that was really impressive that he was able to do all of this with code generation and had very little to write by hand besides the relatively little amount of code in generate raw. And then one last one that I and my team have worked on is Lucet Validate. So Lucet is, rather than a JIT, it's an ahead-of-time compiler for WebAssembly. And so we want to be able to validate a WebAssembly module, that it fits a certain specification before we compile it and then try to load it into our runtime and discover on a totally different computer that doesn't happen to be compatible. So we have this to validate it up front. And this just takes in a WebAssembly module and a WitX spec, and it says, I believe this is ABI compatible. It can't check all the types because a lot of them are erased by the time they make it into a WebAssembly module because WebAssembly doesn't quite have interface types throughout the whole tool chains yet. So that's something it will do eventually, but right now it does its best. So is WitX successful so far? I mean, I'm biased. It found inconsistencies in the WASI spec itself. So the main reason I wrote WitX to first, that default command just validates, is because the first thing that happened was Dan took the C header and wrote a WitX file before there was ever a way for a computer to read it. And I said, okay, I'll write a program that can read it and try to validate it. And I found like 3 typos. So that's good. It saved the implementers some tedious work. I think the real story is that all those use cases I was just talking about, we're able to use code generation, and we're able to keep on upgrading the spec because now that's relatively little maintenance for us. The 2 things I'll say that haven't succeeded yet, all the users use this one WitX Rust crate. That's the only implementation. To be a real standard, you should probably have more than one implementation. So I would love for folks in other languages to create other implementations so that people who aren't in the Rust ecosystem benefit from this. So I'll say, please come use it. Implement your own if you want to. Please get in contact with me. You can, I probably should have put my email. You can find me on the internet. And on the Git issue tracker would probably be the best way. And please ask for help if you need anything to understand using this tool. And I wanted to finally just say thank you. Tons of people contributed to all the use cases, all the development of these tools and ideas. These people and probably even more that I've forgotten. So thank you very much.
All right. So